Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online NPTEL structural geology course. We are learning fractures, joints, faults, and in this lecture we will start faults and faulting. This is part 1 of this lecture and this is lecture number 29. So, in this course we will cover bits, so we will faults. So, we will start at the very beginning, that why we have a structure like faults, and then we will see the brittle, ductile and brittle ductile type of faults. Just we will start showing you how these things do occur in nature. Then we will directly jump into the brittle faults. So, we will start with the anatomy of the fault systems, what the different morphologies, geometries and so on. Then we will classify the faults and also we will give the description of the faults and their structures. And then we will move to the we will discuss a little bit on the typical characteristics of normal faults. The thrust faults and strike safe faults we will discuss in the next lecture. So, you have already learned what is fault. I have shown many illustrations, many diagrams, and also from other lectures you may have a little bit of familiarity what is fault. Now, one part you must have noticed when you are taught or when you learnt about fault, that the deformation in faults, it localizes along a very narrow zone. When we will define, we will see this. But it is always a question and still we do not know the answer, that why deformation localizes along a narrow zone. There are some observations and the best observation comes from the experiment. So, what I will first do, I will try to show you schematically some of the experimental results, and then we will figure it out that why and which domain it is possible to see the faults and under what conditions, what type of faults we can expect. So, let us start with the diagram. So, on the vertical side we have stress, this is a simple stress strain plot, and horizontal side we have strain. Now, at the very beginning we have undeformed sample, and we know that initially when you load a sample, it undergoes an elastic deformation. So, in the elastic deformation goes on, it shortens a little bit. So, the rock would shorten in this direction and also extend in this direction just because of the elasticity, and then it continues deforming following this red curve, which is the elastic curve. Now, after this part there are many possibilities. So, I show you the one possibility first, that is that the rock is deforming in brittle manner. We saw it in the previous lecture. So, it can either fail in mode 1, that means producing tensile fracture, or it can produce mode 2 fractures or shear fractures. So, here if the curve is something like that, that it reaches the yield stress and immediately after it produces a failure type of curve, and therefore, we interpret that in this domain we expect a brittle type of deformation, and the expression of this brittle deformation is either mode 1 or tensile mode or shear mode. Now, we will see soon that this shear mode actually is very similar what we call fault in large scales. Now, if the deformation continues, for example, if I have enough pressure and also a little bit of temperature, then we know that it would show a little bit of hardening. That means, to deform the rock we need more stress, and the rock deforms in homogeneous manner, and the deformation after this yield stress is permanent deformation. So, it shows some sort of barreling, that is the characteristics of the experiments. Now, if the strain further continues and the rock does not produce any fracture, then the homogeneous plastic and permanent deformation continues, and it goes this way with more and more stress requirement. So, we have seen two possibilities. One, that the rock may fail in brittle manner, or it may continue showing homogeneous deformation without producing any fracture, and this is the second type of deformation. Now, a third possibility is there. We have learnt in our deformation mechanism class that it can show strain softening. So, here this is strain hardening, and there is another possibility that we can have strain softening, and if that happens, then we see a localization here in the sample, and this localization or this shear surface here that we see here, this is characteristically different than what we have seen here in the brittle domain. So, this is ductile because the rock is accommodating deformation without producing any fracture, and this is brittle. So, we see three possibilities here. Now, what happens here at this stage of the deformation? The sample is little confused. So, it tries to understand that whether I should distribute the deformation I am receiving entirely on the sample, or I find a zone, a narrow zone where I can channelize all the deformation, and rest of the body of the rock sample can remain virtually undeformed or less deformed. Now, the same thing happens here, but here it happens in brittle manner and here it happens in ductile manner. So, you see that when the deformation is actually under compression, we can have possibilities of brittle deformation in mode 1 or mode 2 manner. We can have possibilities of homogeneous deformation, and we can have possibilities of ductile shear localization or heterogeneous plastic deformation, which is also permanent deformation. So, clearly if we continue with this kind of deformation, then we do not see any localization or faulting like features. So, we are restricted ourselves now in brittle and ductile domain, that where localization is happening either in brittle manner or in ductile manner. Now, when you have localization of deformation along a narrow zone inside the rock sample, we call it shear instability or localization and so on. This is still a problem. People do not know how and why we have localization in the deformation and how it extends the way it is on the earth surfaces or even in a tiny micro scale grains. But we will not go to that part right now. We will avoid this homogeneous deformation part for the time being. We will mostly look at this brittle part and ductile part in the context of this lecture of faults and faulting. So, as we talked about brittle deformation, so the brittle deformation we learned that it does not retain or it does not maintain the cohesion of the rock. So, if this was intact initially, this orange marker in this blue matrix, then because of the shearing, you see that entire rock mass did not deform, but it just deformed along this narrow zone, and therefore, this got shifted and it lost its cohesion. And we can see here some examples. So, this is a large scale field example. You can see that slip happened along this narrow zone, and here we see that we have series of planes along which the deformation localized, and here as well it is a microstructure where we see that because of this brittle deformation the rock lost its cohesion and it is almost brecciated. Now, another extent is of course, as we have learnt, is the ductile deformation, where this orange marker zone did not lose its cohesion. So, it remained continued, and therefore, we see that some examples here, for example, this black layer we can see that it is going like this, or this one as well it is going like this. So, it did not break, it maintained its continuity. If we see in a different scale, we also see that these things are maintaining their continuities. It is not some sort of fracture processes and so on, and this is the image of the microstructure. Now, this brittle and ductile, these two are the two end members of deformation processes. So, whatever happens in between brittle and ductile, we call it brittle ductile deformation. So, that means it receives some sort of ductile deformation and also it receives a significant amount of brittle deformation. Now, how much brittle, how much ductile is a question, is the observation that you have to do in the field or in the laboratory. Now, whether brittle came first or ductile came first, this is again a question of research and observation of specific areas. But if we focus on this brittle ductile part and particularly on this image, we see that these layers, they are a little bit bent, they are a little bit curved, and that indicates that these layers at one point of time suffered ductile deformation, and later it produced the brittle deformation here. You can see here is a microstructure. So, these are some brittle fractures, but at the same time it is producing some other features. We will learn more about it in our shear zone lectures, but these are evidences of brittle ductile deformation. Similarly, we see that here in the matrix dynamic recrystallization is going on, but this large class, we have seen this image before, that these clasts, they are broken and they are slipping past each other. So, it has both brittle and ductile deformation in this. So, based on this idea, we will now try to define what is a fault. So, faults are defined when two adjacent blocks of rock have moved past each other in response to induced stresses. Now, the notion of localized movement leads to the two genetically different classes of faults reflecting the two basic responses of rocks to the stress. One is brittle and another is ductile, and whatever stays in between is brittle ductile. Now, brittle faults, which is commonly known as faults, we generally refer faults as brittle faults. They are fracture discontinuity. So, there must be some fractures. So, cohesion must be lost to define the discontinuity. So, fracture discontinuity along which the rocks on either side have moved past each other in a direction parallel to the fracture plane, and because it is a brittle type of deformation, it is a brittle fault. So, it is a low pressure temperature feature. On the other hand, ductile faults, we do not say it ductile faults, we mostly call it shear zones or ductile shear zones commonly. These are narrow zones of localized but continuous ductile displacement between two blocks without developing or producing any characteristic fractures at the scale of observation. If that happens, then this is a high pressure temperature feature, and we learn about ductile faults or ductile shear zones in the next week, and this week we will focus on brittle faults or faults as we commonly talk about. Now, how these things do happen in nature, how do we understand that where we expect brittle faults, where we expect ductile faults, and as it is mentioned here, this is a low pressure temperature feature and this is a high pressure temperature feature. So, Professor Fossen came up with a very nice illustration that on the surface of the earth or on the subsurface of the earth we have faults. So, this is the expression of the fault on the surface, and if we see on the deeper side at the subsurface we have incohesive fault rocks. That means the cohesion got lost, and slowly we reach to the cohesive fault rocks, and then we arrive the brittle ductile transition, and finally we see here myelonitic rocks. We will learn later what is myelonite in the next week, but these are your ductile faults. And then it anastomoses and widens with depth and so on. So, we have brittle deformation here, we have ductile deformation here, and whatever stays in between, it is brittle ductile deformation. So, this is exactly what is written here, and we also have learned deformation mechanism. So, we can figure it out that in this part this is mostly defined by frictional way and this is mostly defined by plastic way. And when we define the frictional way, we know that we have derived the law Mohr-Coulomb failure criteria, that was shear stress was S plus friction multiplied by normal stress minus pore fluid pressure. Now, this is a linear equation. So, the strength here increases linearly. But here we remember, if you remember the power law, then power law was exponent dependent. So, therefore, this is non-linear, and this particular pattern of the strength profile, shear strength profile of the earth through depth is known as the rheological profile of the earth. We will learn about it later, but this is how the faults are distributed. At the surface, these are brittle, at the depth these are ductile, and in between we have brittle ductile type of deformation. Now, let us talk about the brittle faults and their terminologies. Now, faults, we know that, as we have defined, that it is a fracture discontinuity. So, the discontinuity must represent a plane, and if we have a plane, then as a structural geologist, the first thing is we have to understand what is the strike and deep of this particular plane. So, the fault surface itself defines the fault plane, and if it is a plane, then we can measure the strike. So, in this case, this is a plane and this is intersecting with the horizontal plane. So, this is your horizontal plane. And where this horizontal plane intersects the fault plane, this blue plane is a projection of the fault plane. So, that defines the strike line, and the angle it makes is the deep angle. We have learnt about it. Now, there are very interesting terminologies related to fault rocks or faulted rocks. So, the rock mass which is immediately above the fault plane, and that tells you that fault is not vertical, that means the deep is not 90 degrees. In that case, anything above the fault plane we call it hanging wall, and anything below the fault plane we call it foot wall. And these hanging wall and foot wall, these two terminologies we will use continuously and also professionally if you continue geology or specifically structural geology. There are a few other terms let us talk about. In outcrop scales, faults generally, as I said, that these are mostly straight planes. However, faults are really large scale features, and in general they are curved in large scales, and these are mostly revealed by 3D seismic reflection data. These fault corrugations thereby identified and attributed to the linkage of fault segments through time. So, when the fault is curved and concave upward, then it is gradually flattens with the depth, that means the deep generally reduces with depth, then this is known as listric fault. We will see the diagram soon. If the fault deep is greater than 45 degree, then we call it high angle faults, and if the fault deep is less than 45 degree, then we call it low angle faults. There are some other terminologies. As you can understand that fault is some sort of, you have to have a displacement along the fracture surface, and there it is different, and it is exactly where it is different from joints, because in joints we do not have any displacement along the fracture surfaces, but in faults, yes, we have displacement along the fracture surfaces. Now, imagine if this displacement is large enough, then where actual rock was originated can travel kilometers after kilometers and rest in a different place. If that happens, that rocks that have been translated great distance away from their original site, these are known as allochthonous, and then they come to rest on some rocks, those are actually resting on their original location, and these are known as autochthonous rocks which have retained their original location. Now, in this context there are two other terminologies, one is window and another is clippe. So, imagine that this one of the fault blocks traveled a lot and staying somewhere as an allochthon, for example, this bluish material here, and now this can get eroded and can expose the autochthon rock in between. If that happens, then this is known as window. And in a similarly, if it stays in a little higher topography and stays in an isolated manner and erosion made it staying isolated, then the sheet is completely surrounded by autochthonous material. What we see here, these are known as clippe. And these are terminologies generally those who work in large scale orogenies they use, but it is important that we know what is allochthonous, we know what is autochthonous, we know what is window or fenster, and we also know what is clippe. Now, there are some other terminologies associated to the faults, and these are mostly kinematic terminologies, and this is what we are going to learn now. First, I define this, I read these texts, or I just explain you what it is, and then we will look at these diagrams. So, net slip is the direction of movement of the hanging wall relative to the foot wall. This term relative is very, very important here. The length of the net slip provides the amount or magnitude of displacement on the fault, which generally is the addition of several movements. So, what we see here, if we just have this example, so we see that this point and this point, they were together at one point of time or before the fault happened. Now, fault displaced this point from here to here. So, these 2 points which were neighbors at one point of time, now they stay far away. Now, along which this displacement happens, this is a vector, and this vector is known as net slip, which is A. You can see here a zoomed diagram here. So, this was these 2 points were together, now they are separated along the fault plane, and the vector of this displacement is known as net slip. If this net slip happens along a particular direction, then it is possible that we can resolve the component of this net slip vector along the strike of the fault plane and along the dip direction of the fault plane. So, these are B and C. So, the components of the net slip along the dip and strike directions are dip slip, which is B in this image. So, its component along the dip direction, and then strike slip, which is C, the component of the net slip along the strike direction, and these are known as dip slip and strike slip. Now, we have also an offset because of this fault. So, when we see a planar feature, for example, this surface, we can consider this horizontal surface is a planar feature. Now, this horizontal surface is now resting here. So, it moved down. So, the magnitude of the movement, if you measure vertically, then this is known as throw. So, in this case is this distance, which is marked by D, and the horizontal displacement, if there is any, then this is known as heave, which is marked by E. Now, clearly we can see that the fault movement can be in the sense that you can have dip slip 0 and you can have only strike slip. At the same time, you can have 0 strike slip and you can have the dip slip component only. So, net slip can vary from the strike slip to dip slip along a fault plane. Now, sometimes we use another term which is called separation. We will talk about it later, and this is very important, but at this time please understand that dip separation or strike separation are not equivalent to the dip slip or strike slip respectively. We will learn about it soon. So, based on this slip on the fault plane, we can define the faults in 3 major categories. The first category of the brittle faults, of course, is dip slip faults, the second category is strike slip faults, and third category is oblique faults. We will learn their definitions very soon in the next slide. Within the dip slip faults, we have normal faults and river faults. Within the strike slip faults, based on the sense of the displacement, sense of the strike slip displacement to be specific, we have dextral faults and we have sinistral faults. So, let us look at their definitions. So, as I said that deep slip faults are classified in two sections, one is normal fault and another is reverse fault. So, normal fault we can define it now is a high angle deep slip fault on which the hanging wall has moved down relative to the foot wall. We will see the drawing soon. A normal fault brings younger rocks over older ones. Because of the separation of geological horizons that results from normal faulting, such faults are also termed extensional faults. We will see that. The reverse fault is on the other hand is a deep slip fault as well, on which the hanging wall has moved up over the foot wall. So, consequently, older rocks are brought over the younger rocks. A thrust fault is low angle reverse fault. So, generally the angle is 30 degrees. If the fault deep is less than 30 degrees, then we call it thrust faults, and if it is more than that, then we call it reverse fault. The strike slip faults usually have very steep or vertical dips, and the relative movement between the adjacent blocks generally is horizontal, parallel to the strike of the fault plane. Large strike slip faults are also referred to as transcurrent faults and or range faults. We'll talk about it later, this transcurrent and range fault. Then oblique fault is something that combines the deep slip and strike slip fault. So, it is a combination of strike slip fault with normal or reverse slip components. Let us see what is the normal fault. A normal fault, as we have defined, is a high angle fault on which hanging wall moved down past the foot wall or relative to the foot wall. So, this is the hanging wall. So, first define the fault plane. This is the fault plane here, and it is going down as well. So, this block has moved down in this direction relative to the foot wall. So, this is the sense of displacement as it is marked by the red half arrows. So, this is a normal fault. Now, we see that this is a pure deep slip normal fault because it does not have any strike slip component, or in other words, if I try to draw the net slip here, the net slip is moving like this, because this point and this point were together at one point of time before the fault. So, this displacement happened or this slip happened along the deep direction of the fault plane, and therefore, it does not have any strike slip component. So, therefore, this is a pure deep slip fault, and in that case the hanging wall moved down relative to the foot wall. Now, talking about this younger rock over the older ones, we can see it here, but let us do it in other ways, because this has gone down. So, this would be a topographic high in the system, and if this is topographic high, this would erode with time, and if it erodes, then it would stay like this. Now, if you do a field work, you can figure out that you are walking in this rock, and then if you walk along this side, then you will encounter a contact with another type of rock which is younger than this. So, your younging direction you may plot in the field like this way, but this is not a true lithological contact, this is a faulted contact. The lithological contacts are actually here. So, you have to look here and there to figure out that whether this is a true lithological contact or this is a faulted contact. There are some features here that actually would tell you that this is a faulted contact, but not a lithological contact. So, this is a kind of unconformity. But what I wanted to say that if you drill a log here, you will see that this is younger rock, then younger rock, then younger rock, and then older rock. So, it brings the younger rock over the older ones. So, it maintains the normal stratigraphy of the rock. As I talked about the listric fault, you can see here that if the scale is very, very large, then it is not just a straight plane. At depth, the deep of the fault changes, or in specifically dip of the fault reduces. So, the fault in section appears like a curved line, and this is known as Listric fault, particularly applicable for normal faults. So, here is an example, a field photograph of normal fault from Peru, and you can see here these are the horizontal bedding planes, the traces of the horizontal bedding planes, and this is separated by this fault line. So, we are seeing this in a vertical section. Okay. So, where the beds were horizontal, bedding planes were horizontal, and this got separated this way. We see also another normal fault here, but not as spectacular as it is because of the slip. So, it was here, and the net slip from this you can calculate from here to here. So, this is an example of normal fault. Reverse fault, as we learned, that it is a deep slip fault essentially, on which the hanging wall has moved upward and over the footwall. So, this diagram illustrates that. So, we have the same footwall, but hanging wall, unlike normal faults, instead of going down it moved up. So, that is why the arrow is given, half arrow is given this way, and the footwall relatively moved below the hanging wall. So, when the hanging wall moved upward relative to the footwall, the fault is a reverse fault. And again you can figure out that there is no strike slip component, whatever component it has. So, it was here and now it went here. So, you can figure out this is the net slip, and this net slip here is entirely deep slip. In a similar way as we have looked at in the normal fault, now this is a topographic high, this region, and this can erode out, and if that erodes out, then we have a feature like this. And again, if you start walking from here and do the field work, you may find an older rock, because you are here on the younger rock and then you arrive to an older rock, and then there are some features by which you can identify that this is a faulted boundary or faulted contact. This is not a lithological contact. Interestingly, if you drill here, you make a borehole, you figure out that you have first older rock and then you arrive to an younger rock here or here. So, that is the characteristics of reverse faults, that it brings older rocks over the younger rocks. Here is an example of a spectacular thrust fault from Utah. So, you see here that this is the fault plane, most likely it goes like this, it is not a single line here. So, this suite of layers, now it is here, so it moved this way. So, this is your footwall, and this is the hanging wall of this fault, and hanging wall move upward with respect to the footwall, and therefore, this is a reverse fault. Strike slip faults, as we talked about, that the deep of the strike slip faults are generally steep or almost vertical, and the relative movement generally happens along the strike. And what we see here, that this is an example, this is an illustration of strike slip fault, and here the movement is dextral. That means, if I stand here and try to look at it, then I see that the block away from me is moving towards the right side, and when that happens, this is we call dextral displacement or dextral sense of shear. Now, what we see here, that this point and these 2 points were, so this point and this point, they were together before the faulting, and now this point has moved to this place, right. So, this is the net slip, and there is no deep slip component. So, entire slip component is strike slip component, and therefore, we assign it as strike slip fault. Now, because the markers, these bedding planes, in this case they are horizontal, if this part gets eroded, though this is not topographic high, but for the sake of argument let us consider that this part is eroded, then it would look like this, and you do not see any offset on the vertical side because it is a strike slip fault. However, if the beds were at an angle, then you could figure out that this is a strike slip fault. We will see this later. The sinistral strike slip fault is exactly opposite. So, this point it was here and now it moved here, but here the sense of displacement is sinistral. Again, if I stand here and I look, the far away block is moving in which direction, then I will see it is moving towards the left, and if that happens, then this is sinistral. Relative to me, it moved towards the left side, and therefore, this is a sinistral fault. Again, I can erode this part, and we will see more or less the same feature, that we do not have any vertical or deep slip component, and we also can't understand any strike slip component, though we know there were deformation, but because we do not have any marker plane or marker line, we cannot understand that, at least from the field work, that this was a strike slip fault, but there are ways, we will learn about it soon. So, here is an example of strike slip fault, and as you can figure out that if I stand here, then I look at the further part, then it moved left side. So, this is an example of sinistral strike slip fault, and why I understand this, that this part has moved relative to this way, because I have some marker lines here. So, this marker lines shows me the offset is like this. So, this is from an earthquake from California and photograph from USGS, but you see here how does it work. Now, I will take you to another spectacular place where I used to live at one point of time. This is Wairarapa fault, and this is near Wellington in New Zealand, and this is one of the large active faults in New Zealand, and it was responsible for the massive magnitude 8.2 earthquakes. It happened in 1955, and it almost shaken the North Island of New Zealand, and this is one of the largest recorded earthquake in the New Zealand. What we see here, first of all we see a fault scarp. So, this fault is not a true strike slip fault, but it is mostly strike slip fault with a little, very little deep slip component. But what we see here, so this red dot here, dotted line here, that defines the fault plane. Now, what we see here, that this is the river right now, which is flowing like this, which is continuous. If we consider that this part is fixed and this part is moving in this direction, then what we see, that this river was initially here and it was flowing like this, and then the river in this side got moved, then it was flowing here and now it is flowing here. So, the river is continuously shifting, and this has been dated to be of pre-1855 earthquake, and this is a classic example of dextral strike slip fault. And why this is dextral? Exactly because if you stand in this side, you will see that this is moving towards your right side. Now, oblique faults, when you have both strike slip and deep slip component in your system, and it can be either normal deep slip component or reverse deep slip component. So, here the illustration is for the normal deep slip component. So, if I consider this is the fault plane, this one, then this is the hanging wall, and this is the foot wall, and these 2 points were together before the faulting, it moved this way. So, we can figure out that this is the strike slip component and this is the deep slip component. So, it combines, its net slip combines both strike slip and deep slip component. Therefore, this is a oblique fault. And here we see if we can erode this topographic relief and also this side, then it appears like this, and we see that because it is a normal oblique fault. So, we see it brings the younger rock over the or above the older rocks, but if it is a reverse dip slip fault, then it would make the opposite scenario. That means, it would bring the older rock over the younging rocks. Now, there are few other typical faults, and these are known as scissor faults. So, this one is a scissor fault, that one fault block can rotate around an axis perpendicular to the plane of the scissor fault. So, for example, this one, so there could be an axis and this block actually rotated over it. So, it does not have any typical fixed net slip. So, the net slip would vary, and this is you can geometrically analyze by the rotational displacements or movements, but these are scissor faults, and if it happens following a hinge point, then these are known as hinge scissor faults. So, you can see that net slip is varying from the hinge and as you go far away. So, this is known as hinge scissor fault. Now, let us talk about one of the very important parts that I mentioned before, that whatever we learned so far, this normal fault, reverse fault, strike slip fault, scissor fault and so on, these are mostly marked or mostly classified, separated by their slip movements based on their kinematics. And if you go back and see all these illustrations, the bedding planes were always horizontal, but that not necessarily has to be the case always. The bedding planes, because of some pre-deformation, fold, fault or so on, could be tilted, and if the tilting happens and the faults do move either in normal or reverse or in strike slip manner, the separation of the bedding planes may not show you what is dip slip, what is strike slip and what is your net slip component. And therefore, it is important that in the field to study, if possible, 3 dimensionally when you particularly look at the fault. And when you look at this illustration, we will figure it out how dangerous it is just by looking at the separation, concluding the kinematics of the fault, that whether this is normal, reverse or strike slip. So, what we see here, first of all, that in this illustration the bedding planes are not horizontal like before. So, here the bedding plane has a dip, and this is the strike of the bedding plane and this is the dip of the bedding plane in this case. And if this rock block displaced by a normal oblique slip movement, then we know that this would be its strike slip component and this would be its dip slip component. So, I just write strike slip, this is dip slip ds and this is ns net slip. Now, imagine that this fault with time, this part got eroded and then we are doing field work on the surface. So, if I project this on the surface, I would see it something like that. So, on the surface you see this strike slip separation, right. And if you just look at the surface, then you may conclude the fact that the fault is a strike slip fault without any dip slip component. And looking at these 3D illustrations, it is clear to us that this is not only a strike slip fault, but this is an oblique fault. Now, say this fault got an exposure by some river cut or so, something like that, or an erosion, and this vertical surface is exposed. If that happens, then we may see it on the vertical section like this, where this is the fault plane, a trace of the fault plane, right, and we see that it is showing a normal slip component, normal deep slip component. And if the top surface is not exposed, say it is topographically very high, we could not reach there, then just by looking at in the field, I can conclude that this is a normal fault, but again this idea is wrong. So, the message I would like to give you with these illustrations, these two particular illustrations, that just do not look at the separation. So, this is known as separation, that when you have a planar feature is offset by the fault movement. So, this offset is known as separation, but that not necessarily indicate that this offset is also the kinematic parameter, or it does not lead you to conclude about the kinematics of the fault surface. So, the strike slip or deep slip evidently depends on the net slip, that is for sure, but the strike separation and the deep separation depend both on the net slip and at the same time orientation of the bed with respect to the fault plane. For example, a bed may show a strike separation even if the strike slip is 0. I try to draw it, but you can also try it by yourself. So, for example, I can consider a fault like this. I draw a normal fault. Okay. So, if there is no marker, nothing, this is a normal fault, no problem, but if I have the bedding plane, something like this, and here say then it would go this way, is something like this. That means the bed is inclined and has a dip. And again, if this part gets eroded like this, then what we will see in reality or in the field this is a trace of the fault plane, and on this side we may have something like that. But the vertical side is not exposed. So, on the horizontal side, what you see that it is so you see that this is indeed a deep slip fault. This is a normal fault without any strike slip component, but you see here this is showing a strike slip fault. So, be very careful. Now, again a bed may show a deep separation even if the deep slip is 0. So, for example, you are having a strike slip fault and it is showing a deep separation. So, you can try this drawing. Even if you can have a deep slip fault, but you do not see any deep separation. So, all these things are possible, and the fault may have a large net slip, and yet a bed may not be affected by the fault, and it may not show any offset or any separation on either sections. So, I have given you just an example, and you can try these all possibilities, try to draw that which way the bed should be oriented and how this can happen. I give you one more example. For example, I have again say for example an oblique fault is happening, I am not going to complete the entire demonstration, this is for your idea. So, we know that this is the net slip. Okay. Now, you can figure out if your bedding plane is dipping exactly the way slip happened. So, it is parallel to the slip direction. Then you can guess that if this part gets eroded, you do not see any separation. So, but you have a significant magnitude of net slip. So, this you always remember when you look at faults in the field. So, these are beautiful structures, look at it, try to interpret it, but when you conclude about their kinematics, that what is the dip slip, whether this fault is normal fault or strike slip fault or reverse fault, do not do it just looking at separation, unless you are confirmed by a third dimensional observation. Now, we will see some special type of normal faults, and we will sort of name them, that how do they occur in nature. So, normal faults we have seen so far that it is one sided, but it is possible that normal faults may happen either converging to each other or diverging to each other, and both of them could be normal faults and they can stay there as conjugate sets. Now, when the normal faults dipping away from each other and then they create an upthrown block, this is called horst. So, as you see in this illustration, so it was initially straight layers, and then it had a normal fault in this side and another fault in this side, and they are dipping away from each other, or their dip directions are opposite. So, here it is dipping this side, and on the other side it is dipping in this side, and this particular feature, this topographic elevation, is known as horst, and these are conjugate sets of normal faults. If the opposite happens, that means the normal faults dipping towards each other, then they create a down thrown block, and this is known as graben. So, again you see that this part went down this way and this part went down this way. So, these are two normal faults again in conjugate sets, but they are dipping towards each other. So, this fault is dipping this way and this fault is dipping this side, and therefore, the block in the middle pushed down, and this is known as graben. You can also have something called half graben, where you do not form the other conjugate set, but one set is extremely prominent, and these are known as half graben. You may see some sort of subsidiary faults here, but the major or master fault is this one. We will see this soon. So, this is known as graben and this is known as half graben. Now, there is also one very interesting nature of normal faults, and we call it domino model. Now, domino is something that kids do play, or even adults play as well. So, you remember that we have little blocks like this, we align it like this in a different way, and then you push from this side and then they slide and they stay like this. So, this is called domino or dominoes. Now, in normal faults it happens in a very similar way. So, sections through a rifted portion of the upper crust typically show a series of rotated faults. So, that means you are having normal faults one after another, and the fault blocks arranged more or less like the domino bricks or overturned books in a partly filled bookshelf. This analogy has given rise to the name bookshelf tectonics or the rigid domino model. So, you have books in the bookshelves, there you make them space in between, and then you arrange one after another, and then if you tilt from one side, then the books will rotate past each other and they will make a shape something like this. So, this is a rigid domino style fault blocks. So, initially it was like this, and then it can take the shape of like this, and in the other way you actually can tilt them back. So, now it is 30 degrees, but you can tilt them back to match this layer with this layer and this layer and so on, and then you can figure out what is the initial orientation or initial angle of the original deposition. Now, this also happens in large scale tectonics, particularly when you have rift tectonics. So, here we see that maybe a plume is coming here or some extensional tectonics is happening. So, it produces large number of normal faults, and eventually they tilt and they produce features like this, and these are all kind of domino structures that are characteristics of normal faults. And then we have, as we talked about, we can have master and subsidiary faults. So, once you have a normal fault, and then the other block may or may not show some sort of rotation, and if it cannot rotate properly, it produces a series of subsidiary faults. It can happen both in hanging wall and also in foot wall. It can happen both in normal faults and also in thrust faults. So, the largest fault in a faulted area is known as master fault, and these are associated with minor faults that may be antithetic or synthetic. An antithetic fault dips towards the master fault, while a synthetic fault dips in the same direction as the master fault. Now, these expressions are relative and only make sense when minor faults are related to the specific larger scale faults. So, it can happen in a different generation. In that case, we have to be very careful to name them as either antithetic faults or synthetic faults. So, the first example here, first illustration here, this is a modified version from Professor John Pierre Boog's illustration. What we see here, that this is the master normal fault, and then it produced a synthetic subsidiary normal fault. So, this spelling is wrong here, it should be subsidiary. Okay, so, everywhere it is wrong. And then you see that we have normal faults, but the dip is on the other side. So, therefore, these are antithetic with respect to the master normal fault. In the thrust fault, it can happen in a very similar way. So, this is the master fault you can consider, and then we have same dip direction, a similar dip direction of this synthetic thrust faults, but on the other side we have antithetic faults where the dip direction is opposite to that of the master fault, and these are sometimes known as back thrusts. So, these are very, very important in a fault system, that you have to identify what is master fault and then what is subsidiary faults and whether they are synthetic or antithetic. So, with this I conclude this lecture, and also this is the last lecture for this particular week. A few of you have complained that fold week was very, very long. So, what I decided that the thrust and strike slip faults will spill it to the next week in the lecture week of shear zones. So, we will start with this thrust and strike slip faults in the shear zone week, and then we will go to the shear zone lectures. So, till then have a nice time. I will see you in the next lecture. Thank you very much.